No. Pi is not in the denominator. It's like 8/3 times pi, 7/3 times pi, 1/5 times pi. Good question. All right, quickly while you're working on that, we're well into the second week of classes here, so I have to ask, who's got engaged so far? You have? Congratulations! A year ago when I was teaching this class, a couple got engaged, two of the students, they met in this class. And by like late November or something, they had got engaged. So, pretty cool. I've actually had lots of couples get together in my calculus class. I don't know why that is, but okay. So this section's on volumes. The next section's also on volumes. It's going to be a different technique to do volumes of revolution. A quick word about the applications that we do in this class. The applications that we do in this class are not necessarily the most frequent, nor the most important applications of antiderivatives, of integrals. We picked them because the science or the context, like volumes, is not too hard, and it gives us a variety of contexts to think about how to chop things up and put them together in an integral. So an integral, remember, you can think of it as an accumulation function. It's adding up pieces of a bunch of things. These are really good practice for us to think about how are we going to chop this up and know how to set up the integral. If you go through these application sections trying to memorize the formulas, you're not doing yourself a lot of good. One, because they're probably not going to be formulas you need later, and really what you're supposed to be getting out of these is how to think in a context to how to chop it up and how to set up the integral. If you're good at doing that, you have to memorize very, very few formulas in this class. So, okay, so here's some examples. Volumes. In this section, we really look at volumes of slicing. Volumes of slicing, when you have a revolution, those slices become circles or discs, but not all the time. So here is a shape. The base is a circle. Each slice is actually an equilateral triangle. So we could do this. We could set this up as an integral. We could approximate. We could chop it up this way into however many pieces we wanted, and we could approximate it with approximate each volume of the slice with a small thickness and the area of an equilateral triangle. If it was always the same equilateral triangle at any slice, we're back to we don't need calculus. You just calculate the area of the equilateral triangle and multiply by the height, and you're done. But we have a calculus problem here because that area is changing at each slice. So here we have kind of a funky base. It's two parabolas, and the cross sections on the slices this way are squares, and so that's one representative. That's one representative. Yeah, that didn't make a lot of sense. So there are those. Here we actually have the same base. So these are the same base, but the slices are equilateral. I'm not equilateral. They're semicircles. So here we have a square base. It's partially cut out, but here the square base, but the slices are perpendicular to a diagonal, and the slice is a parabola. So these we can set up as integrals as long as we can find the area of each slice. Then we can do that. So we want to think about which ways does it make sense. If you take this piece and you slice it this way, you always get squares. If you slice it this way, you get some crazy shapes, so it's a lot harder to set up an envelope. Here's an example of a volume of revolution. This is a paraboloid, so it's a parabola. It's just y equals x squared. Well, either like this, you know, y equals x squared, and it's spun around, revolved around an axis. And here, this is a shape. I think this is also a paraboloid or a parabola on one side here, and it's rotated around a line that isn't the axis. So when we calculate this, there's a couple different ways. The way we've learned in this section is we would slice it this way, and you would get these things that look like small washers. And for any of these things, you can calculate the volume, assuming a constant width. These don't have a constant width, but one of the really nice things about calculus is if you can just get close enough, you can get exact with the limit. So it's really nice. You don't have to be exact, but when you throw the limit on there, you end up with exactness. Really nice. There's probably a gospel analogy in there about becoming perfect. I don't know, but so here this isn't exactly a washer with a constant thickness because over here on the edge it's slanted, over here on the edge it's a little slanted. But we could approximate it and just assume that it's constant width everywhere, and calculate the volume of each of these and start adding them up. And as we calculate, and as we slice thinner and thinner and thinner, we can get the exact. Okay. All right. So anyone need more time? Snap if you need more time on this. Yeah, I think the TAs wrote it over here. Yeah. No worries. I didn't announce that, so those are the kind of things I would ask. So, okay, take 10 more seconds. Make sure you're chimed in. Okay. I actually never got to my Mario Kart example last time, so I'm going to quickly talk about Mario Kart in areas between curves. So I'll just do it. I'll do it on this page really fast. So let me kill some. So in Mario Kart, when you're picking carts or bikes or whatever, then whatever your vehicle is, then there is a trade-off between top speed and acceleration. You can't get a vehicle that has high on both. The higher your top speed, the tendency is that the lower the acceleration. So this is an example of two carts. That's supposed to be horizontal right there. So we'll call this cart A. This is cart B. So A has quicker acceleration than B, but B has a higher top speed. So talk to your neighbor. Well, let me put some values on here. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10, 2, 3, 4, 5. There's 1. So talk to your neighbor. At what time does B catch up to A? So go ahead. All right, let's do a little snap poll. Okay, I'm just going to start at 1, and we're going to go over. Snap at the time coordinate of the time you think is closest to when B will catch up to A. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so lots of snaps in this area. Okay, still a broad area. Has B caught up? This is a natural place to look here at the intersection. Has B caught up to A at that point yet? No. What does that? That point is significant. What does that mean? Yes, right there. When their speeds are equal. Up until that point, if they start at the same point and at the same speed, well, we know they start at the same speed, or supposed to. A has always had a faster speed than B. So A has to be ahead of B at that point. Okay? So B's still behind, but then after that point, after about 5 seconds, then B has a faster speed. So how far? How are we supposed to think about this problem? If someone has a nice way to think about this problem, raise your hand and let us know. Yes? So this triangle here, okay? So I'm thinking about this area, because that difference is a difference in speed, and every little interval, I can calculate the speed times the speed times the time will calculate a distance. So that this is B catching up right here, and at some point when this area equals this area, then they will be equal. So how do I use this in Mario Kart? Well, my kids early on were not very good at picking karts. They liked high acceleration. I sacrificed acceleration for higher speed, and I would almost always beat them, especially early on. Now they beat me because they play a lot more than me and they're better at picking karts. So I don't practice enough, I guess, but there are more important things to be practicing. All right. Okay, so go beat. Now you know how to beat your kids in Mario Kart. Okay, so let's do this problem. So first thing I'm going to do is I'm going to try to figure out what this shape looks like. I have a y equals x squared. I'll say this is 1. I'll say this is 2. And I have this region. I have this region here that I'm rotating. I'm rotating around what? Where am I rotating? The x-axis. So this is my axis there. I'm rotating it around that way. Well, it doesn't matter which way around, but that's my center. So the rest of my shape is going to look something like this. Be a little bit bigger than that, of course. But and I've got these slices that look like circles. Okay? So that's what I'm looking at. So would it make sense to integrate with respect to x or y in this case? X, y. I mean, or k. I mean, like WHY. Yes? Okay. Nice. So the cross sections, as you slice perpendicular to the x-axis, they're all going to be discs. So we have a nice shape, geometric shape that we can work with there. Yes? Yeah, that's right. It's going to be really, really difficult if you think about a slice of a y here, and you've got like, some weird shape like that. So we could. It might actually call for a double integral, but we don't get to that in this class. We actually did in 113 when I took 113, but we leave that for multivariable calculus now. So let me see if I can take those off. Okay. So we're going to slice with respect to the x-axis. Each slice is going to be a circle. What's the radius of each slice? It's x squared. It's my function. So f of x equals x squared there, my function. And so how would I calculate the area of each slice? So I take the radius and square it. So I'm going to have x squared squared. That's going to be my radius. Okay? And so how am I going to calculate the area at each slice? Oh, I made a mistake. Sorry, my bad. I got ahead of myself. What's sad is I did that exact same thing in my previous class today. So you'd think I'd learn. X squared at any point will give me my radius. At x equals 1, for example, if I plug in 1, I get 1 out. That's my radius. At x equals 2, I plug in 2 to x squared. I get 4 out. That's my radius there. If I square those, multiplied by pi, that gives me an area at each slice. What's my volume? Because really, the way we want to think about this is I'm thinking about a penny shape, right? A small cylinder, very flat disc shape, and I've got a little delta x down here, or the width of that is delta x. So one edge is the shape of a circle. What's the volume of a circle? I'm sorry, what's the area of a circle? Actually, it's 0. You guys know that? Your teachers have lied to you. The circle is only defined as the points, these outside points. And those points don't add up to any area. So the area of any circle is 0. But the area of interior circle is pi r squared. We usually call that a disk. So the area of a disk. So I'm not going to take points off. One of my other students actually said, so if you said find the area of a circle on a test, I could put 0 and get points? And I said, sure. So now I'll have to be careful to say interior of a circle. So, all right. Okay. So volume is pi x to the 4th times my delta x. Really, we should probably think of this as an xi. If we're chopping it up into n different pieces, I've got n intervals. I can think about an x in each one of those intervals that I'm using. So if I had it for each one of the intervals, pi xi to the 4th times delta x, I equals 1 to n. I could do that for any number of intervals. It wouldn't be exact, but it's going to be close enough that when we take infinite number of slices, we'll get the exact volume. This looks a lot like the definition of the integral. And so we're going to be integrating pi x to the 4th dx. What are my bounds? 1 to 2. Those are all of the x values. I'm integrating with respect to x here. So those are all of the x values at which I'm accumulating area. So it'll be from x equals 1 to x equals 2. So, and we're not going to take time to go through calculating the antiderivative and such, but if you do, what do you get? Maybe I will. It's really fast. 1 to 2, so you get 32 fifths minus 1 fifth, all multiplied by pi. Oops. So you get 31 fifths. Okay. All right, any questions about this? So the answer was C, which a really high percentage of you got. So good job for you or your neighbor, whichever one figured it out. Okay. All right, we're going to do a slicing problem. We're actually going to do this one. Okay? So here I have a parabola. The base is a parabola. And each slice is a square. Okay? So my base is a parabola, each slice is a square. This parabola, it happens to be 4 inches this dimension. Yes? So you can see, yeah, you can see the square here. Each of these, this is a 4 by 4 square. The distance from here to there is also 4 inches. Okay, so this would fit inside a 4 by 4 by 4 cube. So a 4 by 4 by 4 cube would have a volume of 64. So we're going to take a guess before we calculate. What is the volume of this? So just tell your neighbor, I should have brought a treat. I do have one Good and Plenty treat, you know, just one little Good and Plenty stuck in my office or something. But should have brought a treat for whoever gets close enough. So take a guess. Just tell your neighbor your guess. All right, just throw out some guesses. What did you say? 30, 40, 3. What? 41.2. Oh, 31.2. Okay. Nice. We could do like an over/under thing, but so I'll let you guys work on this. You can decide how you can put this parabola, how you want to put this parabola on here. It's up to you. You can put it this way, think about it as a square root function in terms of x. You can put it this way and think of it in terms of y equals x squared. You could think of it like this way and take a negative x squared plus 4 or something like that. So I'll let you guys work with that. You can decide how to put it on, decide how to chop it up, see if you can calculate that with your neighbor. Okay? So go for it. And if you want, we've got a few of these. You can look at these. So fantastic. Raise your hand if you want this one. Anyone else? Take a catch. Can I throw? Ooh. Do you and your neighbors get stuck? Raise your hand. We've got TAs around who can help you out. So the square is 4 by 4, and the height of the parabola is 4. Well, it's 6 or 7. 4 by 4. Let's figure out. were a few different ways I've seen people setting it up. So lots of different ways to set this problem up. Something about which way are you slicing, how to calculate the area. All right. I know some of you are still working through this. I'm going to go ahead and start writing out my work on the screen. So you can keep working on yours if you want. Is it still on? Yeah. Oh, that's my recording software. I'm trying a different recording software today than last time. Oops. All right. So you can set this up a lot of different ways. Some of them turn out a little bit easier when it comes to the number of terms you have to find antiderivatives for, and some of the arithmetic you have to do when you're evaluating. It turns out nicely to do the square root of x. You might not know that from the beginning. I've just done this enough. I know that. So I know it's just y equals square root of x, or you can think about it as like y equals x squared, or x squared minus 4. Why? Because if I plug in 4 here, so the shape is 4 inches long from the vertex of the parabola to the end of the shape. And I know it's 4 inches this way, too. And so this needs to be 2, and that's exactly what I get out when I plug in 4. The x coordinate of 4, I get out 2 there. So I don't have to scale this. So I can just deal with y equals x squared or y equals squared. And we're good there. In inches, anyway. If we did it in feet, we might use it in square. So, and if you look at the shape, which I don't have, so I got a shape maybe. That's it. Okay. So here's the parabola. The slices this way are squared. Okay. So they slice this way is squared. So I'm going to be slicing along the x-axis. So I'm going to be adding up squares, adding up and accumulating volume as I go along the x coordinates. So this is an example of me trying to draw a square that comes out of the paper, but it's really hard. That's why you bring 3D fingers. So what's the area of the square? Well, it's the side times the side. But one of these sides, the square root only gives me half of my side. So I have to double it to get the full side of it. So if as I double it, and then square that, so 2 times the square root of x, or one particular x, will give me that length. And if I square it, that'll give me the area. Multiplied by a delta x will give me a volume, and in the limit, it becomes 2 times the square root of x dx. Okay. What are all of the values where I'm accumulating volumes or areas? 0 to 4. So I'm getting slices all along here where I'm accumulating. I start at 0 and I end at 4. So my bounds are 0 to 4. You go and you work it out, you get 32. Okay, questions? Yes? So you may have rotated the shape, right? That's actually, we're getting to that problem. So in this case, like you may have taken that shape and taken this and revolved it around that axis, and so then you wouldn't have squares as slices, the cross-section slices. You would have had circles. So. So we're trying to find the volume of this shape, where the base is parabolic, but the slices are square. So we have to think about, at each slice, I better have the area of a square for any. So, did you have pi times the square of x squared, or something like that? Or pi x or something like that? Yeah. You knew the problem that was coming up and already did that problem. That's really impressive. So, okay. All right, other questions? Okay. Let's do, before we move to the next problem, I want to talk about an upcoming project. Do we have Project 1? Do we have a Learning Suite quiz up for Project 1? Okay, so you can go to Learning Suite. It's under exams, but you can go click on exams. There will be a 1-question quiz that asks, did you read that? And I actually have an apology to make. I put up the wrong reading. It was still a good reading, I'm sure, and it still applied to calculus, but it actually wasn't the one I intended to put up. So I'll put up the one I intended to later. We might have one extra project now. But I know. If it really hurts you, you can slap me on the way out. So, okay, if we go to BYU Learning Suite, then Project 2. Project 2 has to do with finding a volume of revolution of an object that you find. Okay, you get to go find a volume of revolution. Or it can be a volume of slicing. It doesn't have to be a volume of revolution. It's going to be a volume where you can't just use a simple geometric formula to find it out. So, like my TA that's for the last class, when she was in my class, she did a bowling pin. So, find the volume of a bowling pin. A lot of people do bases. But I'm going to show you some cool tools to help you out with this. So if you go to Geogebra, Geogebra is a really slick math tool. It's like Desmos on steroids. It's a lot more powerful than Desmos. You can do a lot more things. Not quite maybe as easy to start picking up, but yeah, Desmos is really nice. Waiting for it to pull up. Come on. Okay, so up here on the left, You have a calculator icon, you have a geometry icon, and you have a spreadsheet icon. That's what that is. So this is a lot like Desmos. When you're on the calculator icon, you can just type in like sine of x, and it will, if you graph it right, if you type it in right. I can't type it in right. Just delete it. Okay, I'm sorry. So try this again. Sine of x. There you go. It'll graph things for you. The little button over here on the left, if you click on it, it'll hide it. If you click on it again, it'll show it. So, but if you find a picture of something you want to calculate the volume of, then I'm going to show you how to do that in Geogebra. So you click on, and there's already an instructional video on how to do this on Project 2 on the Learning Suite. So just underneath it, it shows you how to do this. So I'm going to go through quick. If you miss things, I'm just giving you a brief example. So we're going to bring in an image. So I'm going to choose the file and pick a gourd, because that's what I picked. Come on, gourd. There's the image, and then you can move it around. You can grab the 2 points at the bottom and change the orientation. And you can shift it over. And you can't see the grid, so one thing you can do is go to settings, go to color, and you can make it a little opaque, or a little translucent. Come on. And line it up. You can scale it. You can move your points so you can scale it to get the right measurement. Right? I should know how long this gourd is, so when I actually calculate the volume, I can figure out what the actual volume is. So right now I'm saying this is maybe 5.5 inches. So how's this going to help us? Well, what we need is this curve, right? We need the curve that goes along right up there to calculate the volume. Don't quite have it centered. It's bothering me. So I'm going to put a few points on here. More points is not necessarily better, okay? Just FYI. And then I'm going to go back to the calculator, and I'm going to have it fit a polynomial through those points. I don't know why it's so slow. So what are my points? C, D, C, comma, D, comma, E, comma, F, comma, G, comma, H. And we wait. And there we go. And then I'm going to move some points around. So this is why more isn't necessarily better, because sometimes the polynomials have to do some crazy things to catch where your points are, and sometimes your curvature isn't right. So you've got to move them around. Anyway, it's not exact right now. You can get closer than that. But then you get the polynomial right down here. See, it tells me what it is. I can move that over, and you're like, Brother Corey, that's crazy. It certainly is. But we can let it do the... Oh, I don't know what happened. Ah. My picture disappeared, but luckily we still have our polynomial. So let's actually have it do the integral for us. So my function is just g of x. Well, it's actually not g of x. G of x is just my radius, right? G of x is just the height from the axis up, and I need to square it and multiply by pi to get my what is wrong with this thing? All right. Well, anyway, when it's not giving you fits, this is really nice. So you can actually have it do the calculation for you. So if you don't want to do that craziness by hand, or you can just round to the hundredths decimal place and go ahead and do it. Do you have a question? You just start typing in integral, and then it'll tell you the syntax. So there's a numerical integral. There's also integral between if you want the area between the two curves. These numerical integrals are easy to do. So you just type in your function and the lower bound and the upper bound. Okay. All right. Wanted to show you that. Give you guys a heads up. Start thinking about what you might want to calculate the volume of. Okay. Let's do this shape, this cone shape. So it's actually the exact same curve as this parabola, okay? But it's hollow. So there's actually a cone cut out of the inside. So there's a straight line that goes from the vertex up to this edge. Okay? So I will draw this and see if you guys can calculate that volume. So the square root of x, and then it's a straight line, and you will have to find the equation of that line. So if you still keep it as square root of x, you get something like this, and then you'd have a line that went, well, I guess we'll make that the 0.42. So you have that, and you're going to be taking that area here and revolving it around the x-axis, and you'll get slices that look like that, sort of. It's a little bit better slice. Okay? So, work with your neighbor, see if you can come up with that volume. All right, I put up two options there. These are working. I have this one, pi the square root of x squared, pi times the square root of x squared minus pi times 2 squared, there you go. Or pi times the quantity square root of x minus x over 2 squared. So are these the same? These will not give you the same thing. Okay? These are different. Which one is correct? The top one. This one will calculate if you think of a slice, it'll give me the area of the large circle, and it will subtract the area of this smaller circle. So it'll leave this line. What this one does is it takes the distance here between them, and then it thinks about that as a radius right here and spins that around. And that's not the same. Yes?
Yeah, so minus
4 minus x squared. Oh, yeah, you can set it, if you set it up differently, yeah, you might have something that's good that, yeah, you have different things going on. So, thanks everybody. Have a great day. See you Friday. Absolutely.